Thank you very much for the given time to me. So today I would like to present our research entitled Corrosion Evaluation on Dry Patching Plant-Based Mortar with Portland Pozzolan Cement Binder after 1 year of exposure. This is me. My name is Pinta Astuti together with our co-author Muhammad Nur Faisal and Aditya Yoga Purnama from Universitas Muhammadiyah Yogyakarta and Universitas Gadjah Mada. Its presentation will be divided into 5 parts. The first part is research background and then research objective, experimental program, result and discussion, and the last part is concluding remarks. We are going to start from research background that as we know, infrastructure development in both rural and urban areas has demonstrated considerable advancement over time. So this is some data information of infrastructure statistic from 2024 in each province in Indonesia. On the other hand, also in our expertise, mortar remain an important point of advancement in the construction industry as its application is intricately linked to ongoing infrastructure development. Good quality of mortar can be seen if the mortar can adhere easily, dry quickly, has durability for a long time, and does not cause crack. So this is some information from our previous researcher about the characteristic of mixture of the mortar. Also, corrosion is one of the cause of concrete degradation factor. Corrosion is a chemical or electrochemical reaction that takes place between reinforcing steel and an aggressive corrosive surrounding environment. So this is the illustration of corrosion process on the steel reinforcement inside of concrete. And also here are the anodic reaction and also cathodic reaction process that result the rust stain. And also this is the explanation about the rust stain. Rust stain is a substance that has a reddish brown color with a chemical formula. This is a chemical formula of rust stain, and also iron oxide can peel off, causing newly exposed surface to corrode gradually. So corrosion can compromise the integrity of the building structure, and if not addressed, will reduce the service life of the structure. And then we study several literature from previous research related to our topic today. Next, we move to our second part about the research objective. So the first objective is to understanding the impact of corrosion on our new mortar with the dimension 15 by 15 by 15 centimeter, which include 2 reinforcement embedded on the specimen. And then we want to know the effect of corrosion prevention method by coating technique on corrosion of our mortar specimen, and we try to apply 3 types of coating method on the uncoated steel bar, concrete surface coating, and also steel surface coating. And the last objective is to understand the effect of the concrete cover depth 3 centimeter and 5 centimeter, and also the exposure condition in dry, wet, and dry wet cycle condition. Then we move to our experimental program. So after literature study, then we fabricate our specimen. So actually we have 18 variation of specimen, and Each variation contains three repetition. So here we have using non-waste aggregate. So it means without using the dried mortar from the batching plant here in the left side, and on right side we have the specimen that contain the waste aggregate specimen. So after we have fabricated the specimen, then we measure the corrosion potential value, and this test will be the most important and will be highlighted in this presentation. After that, we continue with other uh, experimental program, for example, crushing the specimen and then conduct the carbonation test. And also, of course, we observe and calculate the actual corrosion value and quick loss of the steel bar. And then analysis and discussion of the test result and finish. So this is our specimen design, and then we applied three type of coating method by using bituminous coating type. So basically, we apply three layer of the coating material into the steel bar, into the concrete surface, and another one without applying the coating method. So this is some picture. Uh, there's some picture from our experimental program, sample preparation, and then crushing process, carbonation testing, and then half cell potential test. Also the result of crushing, and we calculate the actual corrosion that occur on the specimen. And then we move to the fourth part, result and discussion. So here, the highlight of today's test result is about the half cell potential test value of the specimen from 0 day until more than 400 days. So in this slide is presented result of half cell potential test value on no coating steel bar. So the average Hafsa potential value according to STM CA76 indicate that the reading less than minus 200 milliwatts suggests the presence of reinforcement embedded into concrete with a 90% probability of not undergoing corrosion in the measured area. Meanwhile, the HCP value ranging from minus 350 to minus 200 millivolt indicate that corrosion activity cannot be determined with certainty. Furthermore, the use of dried waste mortar reduces the quality of the material, thereby increasing the risk of corrosion beginning at around 250 days. Whereas the specimen without waste material only start to exhibit sign of corrosion at approximately 350 days. And then we move to another test result on the concrete surface coating. So the trend of axial potential measurement for concrete surface coated and uncoated specimen show a similar pattern over time. In addition, applying a coating to the surface of the steel bar significantly enhanced its durability, delaying the onset of corrosion risk by approximately 20 days compared with uncoated reinforcement. And then we move to another coating type, that is steel surface coating. So the specimen treated by steel coating shows a higher half-cell potential value after 250 days compared with both uncoated and concrete surface coated specimen. This occurs because the protective layer directly on the reinforcement effectively suppress corrosion initiation. Additionally, the steel-coated limits ionic penetration and helps maintain a stable passive film on the steel surface, providing longer-lasting corrosion resistance. And then about the three types of exposure conditions. The first exposure condition is in the dry exposure condition. So for all specimen, whether in comparing dried mortar waste or not, none of the protection types showed an increased risk of corrosion. As indicated, perhaps the real value remain above minus 250 milliwatt, indicating that the concrete matrix and protection system were still able to maintain the passive environment around the steel. The exception is the specimen containing dried mortar waste with a 3 centimeter concrete cover where the reduced cover depth and lower material quality accelerate moisture and ion penetration, leading to earlier deposition of the steel surface and a corresponding increased corrosion risk. And then we move to the wet condition. So under the wet exposure condition, the specimen with a dried mortar waste remains stable up to 400 degrees, whereas those containing dried mortar waste drop to a high corrosion risk level as early as day 250. So yeah, this occurs because the inclusion of dried mortar waste increase porosity and reduce the density of the concrete matrix, allowing water and aggressive ions to penetrate more quickly. The continuous wet environment further accelerates this ingress, leading to earlier breakdown of the passive film on the steel and a much faster onset of corrosion compared with the specimen made with the normal concrete. And then the dry wet cycle exposure condition. So under dry wet cycle exposure condition, the half subterranean value are slightly lower than those observed under continuous wet condition, indicating a more severe corrosion risk. This occurs because repeated drying and wetting accelerate the movement of moisture and ions in and out of the concrete, causing frequent expansion and contraction cycle in the pore structure. This cycle promotes microcracking, increase permeability, and enhance oxygen availability at the steel surface condition that collectively intensify corrosion activity more aggressively than constant wet exposure. So yeah, we come to the end of today's presentation. It's about the concluding remarks. So based on our experiment, we derive 5 conclusions. The first, silk coating provides superior protection, delaying the onset of corrosion by about 20 days compared with uncoated reinforcement, while showing a similar half-cell potential trend to other specimens. Second, dried mortar waste reduced material quality, resulting in earlier corrosion initiation around day 250 compared with normal concrete, which begins to show signs of corrosion near day 350. Third, the specimen with dried mortar waste and a 3 centimeter concrete cover show the highest vulnerability as the reduced cover and increased porosity accelerate moisture and ion penetration, leading to early deposition. Fourth, under continuous wet exposure, normal concrete specimen remain stable up to 400 degrees, whereas specimens with dry mortar waste rapidly drop to a high corrosion risk level at day 250 due to their more porous matrix. And the last, dry wet cycle exposure produce even lower half-cell potential value, indicating more severe corrosion because the repeated cycle enhances ion transport, oxygen availability, and microcracking within concrete. So that's all my presentation. Thank you very much.